I have to click the button. Prashant Kumar, and he's a PhD candidate at Oregon State University, just down the road. His current research pertains to developing techniques for explainable computing and implementing these techniques as software libraries and DSLs. So go ahead, Prashant.
Thank you so much, Richard, for giving me this opportunity to talk to you all here. So this is going to be a two-part talk. In the first part, I present my research on explainable computing, more specifically explaining results of dynamic programming problems with value decomposition. And this is joint work with my advisor, Dr. Martin Ewick and Dr. Alan Fern. In the second part, I will be talking about the design of a concurrent programming language called MPL. So I was a graduate student at University of Calgary, and I used to visit the beautiful towns in central British Columbia. So two of those towns are Golden and Nelson. And once when I was trying to navigate from Golden to Nelson, I found something surprising. The path that was shown by Google Maps to be the shortest path was 78 kilometers longer than the alternate. So the path in blue, this is the optimal path, and the path in gray is the foil path. So one question that we may want to ask is, why is it the case that the blue path is better than the foil path or the gray path? So questions like this, where we are comparing optimal solution against the foil solution, questions like this are called contrastive questions in explanation literature. And these kind of contrastive questions give rise to contrastive explanations. So one reason could be there is a national park along the gray path, and there might be a lot of snow along that path, which might be the reason that the gray path is substantially slower. So let's formalize this notion of explanation that we saw here. And for this talk, my notion of explanation will be contrastive explanations. So from the beautiful world of British Columbia, let's get down to the world that we are more aware of, the world of graphs. So the nodes represent the important landmarks in a city, and the edges represent the travel time along between the nodes. For example, the travel time between the nodes 1, 2 is 14 minutes. So the shortest path here is the path 1, 2, 5, 4 of length 30, and the second shortest path is of length 31. And if you look at the red path, the second shortest path or the foil path, it seems like it is the more direct path. So the contrastive question here is, why is the path 1, 2, 5, 4 better than 1, 3, 4? And in order to explain this, we make an observation. The observation is the algorithms tend to forget the underlying structure of data. What do I mean by that? So the travel time of 14 minutes here might be comprised of 10 minutes of pure travel time, 3 minutes of traffic delay, 1 minute of construction delay, and so on. So if we work with this decomposed data and not aggregate these values and simply run the shortest path on that, running the shortest path on the decomposed data gives us, instead of just 30, tells us what is the contribution of the individual components in the shortest path. So the pure travel time, the contribution of pure travel time is 10 plus 6 plus 4, giving us 20. Similarly, we can find the contributions of the traffic delay and so on. We can do the same thing for the foil path. This is kind of revealing here. This tells us that although the shortest, the foil path, the 1, 3, 4, the red path, although it has this has a shorter travel time. So the user is okay to be confused here because the travel time itself is shorter. But if you look at the second component, the 10 minutes of traffic delay might be the reason why the green one is worse. So once we have this intuition, we are now ready to formalize it. So to begin with, what do? We associate all the decomposed components with component labels. So TT stands for travel time, TD stands for traffic delay, CD for construction delay, and WD for weather delay. So when we associate component labels with component values, this is called a value decomposition. So phi O is the value decomposition for the optimal path, and phi F is the value decomposition for the foil path or the red path. Right? And once we have that, we know that both the value decompositions are lining up perfectly. So why don't we go ahead and subtract them? And when we go ahead and subtract them, we have some red components and some green components. Red components are the components where the foil path has an advantage, and green components are the components where the optimal path has an advantage. So it turns out that foil is better in all respects except for the traffic delay. However, this traffic delay seems to be more than enough to compensate for all the overall badness of the red components. So we get together all the red components. These are called barriers for explanation, represented by beta OF, and overall badness of the barrier is phi. We know that green components have to overcome the barrier. That was the reason why the green path was the optimal path. So here we just have one element, one green element. If we had multiple green elements, maybe we did not need all of them in order to compensate for the overall badness of the red components. So the minimal set of components, minimal set of green components, which can overcome the total barrier of the red components, are called minimal dominating sets. So a minimal explanation for why 1254 is better than the red path 134 is the fact that transportation delay along the foil is the reason why foil is not the shortest path. So far, so good. We have not done anything extraordinary. Everything has been reasonably straightforward. But at this point in my research, I got stuck. The reason was, okay, I have shortest path. I implement the shortest path algorithm. Turn it into a version which can explain the results. But what happens if I get a different dynamic programming problem? Do I repeat the same process for all the problems that we get? And as PL researchers, it did not set well with us. So what we did, we realized that dynamic programming problems can be modeled as semirings. So once we have modeled dynamic programming problem as semirings, all you need to specify is the recurrence relation for that dynamic programming problem. And using that recurrence, we will give you, using our library, we will give you an implementation, a DP implementation for your problem, as well as an explainable version of your problem. So before we talk more about how we got about the solution, let's talk a little bit about dynamic programming. So you have a complicated problem, you divide it into simpler problems, and you combine the solution of the simpler problems in order to get the solution of the complicated problem. And the reason you can do that is the optimal substructure property. So, and while you're solving these simpler problems, you are going to store the solution of these simpler problems somewhere, so that once you see the same problem, you don't have to perform the computation again. And DP problems are characterized by the recurrence relation. For example, SP is the recurrence relation for the shortest path between nodes S and B using at the max I number of edges. Right? So every DP problem will have a recurrence relation. Now, a little bit about semiring. So semirings are algebraic structure described by a 5-tuple. You have an underlying set. You have two binary operations, semiring addition and semiring multiplication, shown by circle plus and circle multiply here, and identity element for addition and multiplication. And you have, the axioms that you would expect: associativity of elements, commutativity, identity for addition and multiplication, and the fact that multiplication distributes over addition. And one common example for tropical semiring, one common example for semiring is tropical semiring. The underlying set is the set of real numbers with infinity. Semiring addition and multiplication are min and the plus operation. And we know the identity for min is infinity and the identity for plus is 0. Now, representing all this in Haskell is straightforward. We can define a class semiring These are the two identity elements. These are the two binary operations, angle bracket plus and angle bracket star. And this is the data type large is the underlying set. So finite A is R plus and infinity is the infinity element. And we can easily write an instance definition of large for the semi-ring type class. All right. So what do we do with this newfound knowledge of semi-rings that we have? So look at the recurrence relation that we had for the shortest path. Now, if I just replace the min with semi-ring addition and plus with semi-ring multiplication, we get a recurrence relation shown below. This recurrence relation is also called the semi-ring recurrence relation. So if I just show you this recurrence relation and don't tell you what in which semi-ring this recurrence relation is defined, you wouldn't be able to do anything with this. But here we know that the recurrence relation here is the min plus semi-ring. So we have done a very syntactic transformation, taken a recurrence to semi-ring recurrence. Now we have developed a library where you can take this semi-ring recurrence and convert it to just code. And doing this in a language like Haskell is kind of straightforward. So if you look at our code here, one is just one, semi-ring identity 0 is simply 0. Memo is a recursive call that performs the recursive call, but on top of that is also performs memoization. And semi-ring addition, as we saw, angle bracket plus, semi-ring multiplication, angle bracket star. So all I'm trying to show here is once you have the semi-ring recurrence, implementing it in our library is kind of straightforward. So once we have this implementation, what do we do? Just try finding the shortest path for this particular graph. So we call shortest path on graph G between edges, nodes 1 and 4. And this large double is simply specifying what semi-ring are we working in. We are specifying the semi-ring simply based on the type annotation. Right? But in order to generate explanations, we need more than that. We need a decomposed output as well as paths. So if you look at the type annotation here, we have designed a semi-ring called view semi-ring that gives us the decomposed path as well as decomposed path length as well as the path itself. And once you have that, we already know what the decomposed output is going to be for the path 134 because that is the foil. User is going to provide that. So once we have these two decomposed paths, decomposed output for these two paths, we can use explain with function to tell us that traffic delay is the reason why P is better than P prime. So essentially, what have we done? Traces have been used for explaining output of programs for a long time. All we have done here is we have taken the trace of trace of an algorithm to explain the output of the algorithm. So this library is present here. If any of you may find it useful, that is where you can go. And we have taken this work even further. Here the decomposition structure was linear. So 30 was decomposed into 15 and 15. What happens when 15 can be further decomposed into 7 and 8? And 8 could be further decomposed into 4 and 4. So we have done those things as well, but I'm not presenting it here just because it can get pretty boring and lengthy. So I just wanted to show you one aspect of the work that I have done for explainable computing. And second is, this is MPL. We have designed a programming language called message passing language, MPL, which is a concurrent programming language with type channels. And this work I did as a master's student with Dr. Robin Cockett at University of Calgary. So MPL stands for message passing language, and it's a concurrent programming language. So the difference here is the concurrency primitive is message passing in addition rather than threads and shared memory, which might be the concurrency primitive for other languages. And this introduces MPL introduces a notion of type safety to concurrent programming. And this work is based on a paper by Dr. Robin Cockett and Craig Pastro called Logic of Message Passing. So MPL consists of essentially two languages, sequential MPL and concurrent MPL. And sequential MPL is your run-of-the-mill function language. Actually, no, because it has codata definitions as well, in addition to data definitions. And it allows you to define functions like a normal functional language. And in addition to, concurrent MPL allows us to define protocol and co-protocol definitions. These are data definitions and co-data definitions in the concurrent world. So the basic unit of code in a concurrent program is a process. So process can call other process can call other functions. So all of this may be fairly abstract. So I want you to keep this picture in mind as we follow my talk along. So these circles represent processes. I have 4 processes here, P1 to P4. The solid line between these circles represent a channel. This channel allows any two process connecting it to share information. So here P2 and P3 can share information amongst themselves. They can send a value, they can receive a value along channel CH. Then there are some channels that are connected to the outside world. These channels are called services, and we need services so that a process can interact with the outside world. Right? For example, it can take input from the outside world and it can show output to the user. Then the rectangular box shows a function that can be called by any process. So here the function is being called by 2 processes, P2 and P3. All right, so what do we mean by the notion of type safety in the concurrent world? Let's assume a little bit more about channels. So a channel, when it is connected to 2 processes, for one process, it acts as an output polarity channel shown by plus, and for the other, it acts as an input polarity channel shown by minus. So what do we mean by the notion of type safety in concurrency? Let's look at this diagram over here. We have 2 processes, P1 and P2, connected by a channel CH. Is there anything wrong with this configuration? Seems like both the process P1 and P2, they are trying to receive a value on the channel CH. If P1 wants to receive something, P2 has to send something on the channel, and vice versa. Right? So a setup like this should result in type error. And that is what MPL does. Yeah.
Is the problem that they're both getting right now? Or would it have been okay if they took turns? Like, is it that it should be unidirectional, or just that they should both be synchronized?
They should be synchronized. So if one action is happening here, the dual of that action should happen at the end of P2. So the duality of these actions is the core of the entire point of the type safety of concurrent MPL. So the way we do it is we type in first CH in process P1. We get a type, get a top bot. Top bot simply means is the type constructor corresponding to closing of a channel. A is the type of X. And at the other end, we get a type called put. So CH, since it is the same channel, the type inferred from processes P1 and P2, it should be consistent. Since they are not consistent, we get a type error. So let's look at the get and the put type a little bit more. Here we have a type get a, put a, top bot. Right? So what it means is the channel whose type is get a, put a, top bot, it should first receive a value of type A, then put a value of type A on the channel, and then finally close that channel. Top bot simply stands for top and bottom. So if on channel we are trying to get 2 values and then close the channel, it will result in a type error. If we are trying to put 2 values on a channel, it will again result in a type error. So we saw get put type constructor, we saw top bot type constructor. In addition to that, we have 3 other type constructors, neg, tensor, and power. So we'll look at them as we go further in the talk. But one thing that we have seen in normal functional languages is using basic types, we can define user-defined types or data types, right? So these are the basic channel types. We can use these basic channel types to define very complex interactions happening on a channel. And these types are called either protocols or co-protocols. So before I show you how to define protocols and co-protocols using these base channel types, which are just the data types in the concurrent world, I need to show you some of the syntax. In order to get a good feel for the syntax of MPL, maybe I should show you how data types are defined in concurrent MPL. So, sorry, sequential MPL. So this is the list data type that we all know and understand, right? List has two constructors, nil and cons. This is a polymorphic list, but there's something weird here, right? If we are programmed in Haskell, there's something more going on here, at least in terms of syntax. It says data list A to C. Where is this coming from? This simply shows the fact that a data type is a F algebra. So if you look at the type of these constructors, nil and cons, simply replace C with list A, and you will get the type of nil, which is list A, and type of cons, which is A to list A to list A. For these constructors, the rightmost argument is going to be C. And once we have this data type, we can easily perform recursion on this data type on list in order to find its length. But wait, there's something else. Sequential MPL also provides built-in folds for a data type. We know that folds are unique map. So MPL generates these fold maps for every data type. And once we have the fold map, we can implement our program in a slightly cleaner fashion. Nil still gives us the length 0. However, in the cons, we have 1 plus n. Why? Because the recursive call is already taken care of in the fold case. Now, this is something I don't think most programming languages would have. So in Haskell, if you wanted to model infinite structures, we would use the laziness aspect of Haskell, right? However, if you ask a category theorist what is the right way to implement infinite structures, they will say codata types. So we have an inflest codata type having a type variable A, and we have two. These are called destructors. Head and tail are the destructors. And in the case of constructors, the rightmost argument was C. In the case of destructors, the leftmost argument is C. And we can simply replace C with inflest A to get the type of head and tail. So head has a type inflest A to A, and tail has a type inflest A to inflest A. It will take head will just give you the head of infinite list, and tail will give you everything but the head of the infinite list. And once we have this codata type, I can create a record of infinite list of numbers starting from n, which is what I do over here. Head is simply n, and for the tail, recursively call this function. And once we have that, we can take as many we can generate as many numbers as possible based on the argument to the get numList function using the destructors head and tail. So there is a perfect symmetry between data types and codata types here. Like we had built-in folds for data types, we have built-in unfolds for codata types. So here again, if you compare these and this, there isn't a recursive call in unfolds because that is taken care of in the case of. Okay, so now we have taken care of the syntactic weirdness of folds and data types and codata types. We can look at what data types and codata types look in the concurrent world. So we have defined a protocol called in term with a type variable A And the syntax simply shows that it is akin to data type. And we have three constructors for it. These constructors are also called handles in the case of concurrent MPL or in the case of protocols. So look at the first handle, getInt. GetInt says get a value of type A and recursively call the protocol in turn. So either you can do as many gets as possible. You can do get and put, and finally you can close this whole interaction. So similar to codata types, we have Go protocols here and Go protocol. So one difference between protocols and Go protocols is protocols are used with output channels and Go protocols are used with input channels. And the destructors of Go protocols here are called Go handles. So this is what a function definition looks like. Proc is the keyword for defining a process. Then this is simply the process name. Then we have a process type. So everything before the bar is the type of the sequential parameter of the process. Everything after the bar is the type of the concurrent parameter. So topbot is the type of the input channel, and topbot on the right hand side of this arrow is the type of the output channel, which is CH2 here. So type of CH1 is also topbot, CH2 is also topbot. Now, once you have specified the types, all you can do in this process is simply close the two channels. If you said get something on CH2 and get something on CH1, you will get a type error saying that your process, you have defined the type to be topbot, whereas the inferred type is something else. So do allows us to group together the body for the sum proc process. So what have we seen so far? A MPL program consists of processes, functions, data definitions, codata definitions, protocol and co-protocol definitions. Processes have input and output polarity channels. Every channel has a channel type, and using base channel types, we can define complex interactions happening on a channel called protocols and co-protocols. So let's look at some of the facilities, some of the commands that MPL provides to write concurrent code. So roughly these can be divided into two parts. These are standalone MPL constructs or dual MPL constructs. So most of the MPL constructs, they come as a pair. However, there are some which are standalone. So one of the first standalone constructs are process call. So in the last slide, or maybe the one before that, we defined a process called sumproc. And that process did not have a sequential parameter. So we have to call the process the way we had defined it. It should be the call and the definition should be consistent. Now, plug is a very important concurrent MPL construct. So if you have two processes, P1 and P2, and if you want to connect them together, if you want to make them talk to each other, they need to be connected via a channel, right? Or maybe as many channels as you want. So for example, in the first part, P1 and P2 are two processes that are connected by two channels. What do we do when we want to connect multiple processes? We can connect P1 and P2 via CH1 and P2 and P3 via CH2. And once you have plugged a channel between two processes, it goes without saying that the input type of this channel from both the processes should be unifiable, should be consistent. And a pair of channels, a pair of concurrent MPL commands that we have are close and halt. So in MPL, you always close a channel before you stop the process. So both close and by convention, you close all the channels and halt the last channel. And both close and halt result in the type topbot, standing for top, and bottom. So in the original paper, Dr. Cockett, he had separated the type top and bot. However, it was difficult to program in, and that strong type system had certain advantages. For example, you could not write a program that will go in deadlock with that strong type system. However, for the ease of programmers, we weaken the type system a little bit and we put top board as the same type, and this type constructor is obtained both for close and halt. Okay, so in one of the earlier slides, we saw what the wrong configuration of getting and putting look like, right? Here, let's look at what the right configuration looks like. If P1 wants to get something on channel CH, P2 should be putting it. Right? So and this is CH is output channel for P1. So when we are getting a value on an output channel, the type constructor for that is get, or when we are putting a value on an input channel, the type constructor is again get, and vice versa. When we are putting a value on an output channel, the type constructor is get, and when we are getting a value on an input channel, the type constructor is put. So this,
You might be getting here in the future, in which case it's fine to say I'll get there in the future, but what about error handling here? Like, it seems like you're assuming these channels are fully reliable, but perhaps the operating system, you overflow some buffer and it kills your channel, or you're doing some network request doesn't come through. Does this restrict your error handling in, say, P1 if you go to do the get, but the channel's been closed because of something outside of your control?
no, at least when describing this here, I'm assuming that events like that do not happen. So I've not thought exactly about what would happen if a situation like that occurred. So this is what we have for get put. Then a lot of the times we may want to equate two channels, and when might we want to do that? If you want to put a value on channel CH1, and if you want CH2 to have access to all those values, or if something is put on CH2 and CH1 should have access to all those values, then if we equate CH1 and CH2, that will serve our purpose. All right, so one thing to notice here is when we are equating two channels, one of the channels has to be input polarity channel, other has to be output polarity channels. The polarity of the two channels being equated has to be different. But what if you wanted to equate two channels of the same polarity? We'll use the negation of a channel to make the polarity of these two channels different, and then we can equate them. And the neg command results in a constructor neg. So let's look at an example of a program with identity. So P1, P2, and P3, these are the processes that I'm going to define. And O1 is the outside world shown with dotted line and dotted circle. O2 is again outside world connected to process P3. So this process P1 is going to get a value from a service channel. It is going to put a value on this channel W1. Now this process P2 is not going to put this value in turn on W2. All it is going to do is going to equate W1 and W2. Right? And once these two channels are equated, the value that was put on W1 should be available for process P3 to read from, which it reads and shows to the user on this end. So this is the corresponding MPL code for that. I do not expect you to understand this. All I wanted to show here was, this can be done very succinctly in MPL. Right? This is where I equated channels W2 and W1. This is where we are plugging processes P1 and P2 along W1 and P2 and P3 along W2. Yeah.
Are we assuming that processes only ever have like one negative and one positive?
No, we are not. A process can have as many channels as they want, and it's just the examples turned out this way. They may or may not even have channels.
Okay, like how would that? I mean, maybe briefly, like how would that show up in the types of these processes if they had more channels? Would like their interactions, how they interleave their interactions with those channels show up somehow, or like? Right.
So what will happen if there aren't any channels for? process P1. So your question is, what happens when there isn't a channel over here on the left or the right, right?
I was thinking like there might be two, like I might have a diamond, like the P1 talks to 2 and 2A,
Yeah,
and 2 and 2A talk to 3.
I think I have an example like that.
Okay, well, maybe we'll get to it then.
So if I do not answer the question, let me know, okay? And the next, what happened? So the next pair of concurrent MPL constructs are edge put and edge case. So when we want to put a handle on a channel, why do we want to put a handle on a channel? Because putting a handle on a channel restricts the kind of actions that can happen on a channel. Right? So the syntax for that is on the right of the slide, edge put, H on alpha, where H is a handle and alpha is a channel. Right? And once you have put a handle on a channel, on the other end, the receiving process will edge case on that. It's casing on the constructors of a data type in a normal functional language. So let's look at this example here. So here we have processes P1 and P2, and we are trying to replicate a chat server here. Okay. Process P1 is going to take a value from the user here. It is going to put this value on channel CH. P2 is going to read that value. P2 is going to show this value to the user at the end of P2. Then in turn, it expects the user O3 to put some value on this channel I2, which will be put on CH, which will be put on I1. So it's a very primitive chat if you think, chatting with numbers is chatting. So how do you terminate this chat? So I came up with an arbitrary criteria. If the number input at this point is less than 10, the chat terminates. And this could very easily be done with strings. So this is what the code for this number chat looks like. And this is the stopping criteria. Here we are edge casing on the constructors or the handles of a channel. Here we are plugging the process P1 and P2 via channel CH. And in concurrency, sometimes you want to have a process and you want to fork it into two processes. Okay. So what happens to the channel that was attached to that process? That channel also has to be forked, right? So split allows us to split a channel into two channels, alpha into alpha 1 and alpha 2. And fork can then attach a process P1 to alpha 1 and process P2 to alpha 2. So split and fork will always come in pair. Unless you split a channel, you cannot fork a process that is attached to that channel. So splitting on an input polarity channel or forking on an output polarity channel results in a protocol tensor. And or splitting on an output polarity channel or forking on an input polarity channel, it results in a protocol path. So here, the before configuration is, we have two processes P1 and P2 connected via channel CH. At the end of P1, channel CH is going to be split. At the end of P2, this process P2 is going to be forked into two processes, P2.1 and P2.2. This process P2 has two service channels associated with it. One of the fork process will have this channel associated. The other one will have this channel associated with it. So let's look at the after diagram. Once split and fork happens, P2.1 has one associated service channel. P2.2 has the second associated service channel. And process P2 has been split into P2.1 and P2.2. Since splitting was occurring at the end of positive polarity channel and forking was occurring at the end of a negative polarity channel, the resultant type is T1 tensor T2, where T1 and T2 are these split channels. So in this program, what we have simply done is all we have done is we have taken a number at the end of P2. This number, so at the end of P1, this number is put on channel CH. Then once P2 is split into two process, P21 is going to square that number and show it to the user. P22 is simply going to cube that number and show it to the user. So this is what the splitting of channel looks like. And here I am forking on the split channel CH1 and CH2. This is process P21 and P22. So I was actually hoping to show you some of the interesting programs in MPL, but this was done like 5 years ago, and they have made some breaking changes in GSCI, in GSC in the meantime. So I cannot show it to you, but I really think this was a well-designed language, and two parts of the language especially I think were pretty well done. One was the type system, and one was the abstract machine on which MPL programs were running. So if you want to look at any of these things, you can look at in my thesis, which link I have provided here. And thank you for being such a good audience. I can take any questions if you have.
So you go ahead.
I'll go first. Do you have like an idea of what you imagine like a next step? I guess, do you think this is maybe this type system and like applying it to a bigger system? Like it seems like probably in general, you wouldn't imagine programming in this as it is now and using that in the large, but it seems like maybe, do you think like the thing is to take the research on the types and apply that to like a real system, or is it to flesh out this language? Like, where would you go next, given some flexibility on what to do with this?
So I think the types themselves are very flexible. When there are processes interacting with each other, it seems like this idea could be taken even outside MPL and could be applied to any other place where we have concurrency problems. And I think a lot of the errors in concurrency, when you are receiving a message that you did not expect, or you are things like that, a lot of it could be caught just with the type system. That is one. And number two, what I would do if I was to take it further in terms of a language. So currently, in order to, one of the examples I have for MPL was, there were two terminals and the users were playing tic-tac-toe. If you were making a move, the other could see it, and if in turn they could make a move. So I would try to make it, take it to various terminals. At this point, it is still I think research language, still. So I try to do what basic Erlang programs could do. With basic Erlang, with Erlang you could have chat servers on different machines with very few lines of code. I'll try to replicate something like that with this in a type setting. Okay. Yes.
Ian, you've got your hand up. Do you want to go?
Yeah. I'm wondering if you can help me understand the trade-offs of this design relative to other concurrent languages with types that ensure deadlock freedom. So it seems like because the process-oriented layer of the language is separated from the functional layer, that you can't, for example, send a channel along a channel. Is that right? Because the channels have to be indexed by sequential types. Okay. And then another aspect seems to be that the protocol, like the architecture of protocols, is static in the sense that it can't be determined by the sequential layer. I can't say, have my sequential program decide to use process A or process B and hook it up to process C. Are these elements, these are the kinds of things that you might find in a another process calculus, perhaps based on session types or something like that. How integral is the sort of separation between the sequential fragment and the concurrent fragment? How integral is that to some of the features and other results like deadlock freedom or type safety or whatever? Like how integral are those? Do you have a sense of that? Because it is a deviation from the kind of session typed approach where everything's a channel and you're passing channels along channels and, you know, that sort of thing.
Yeah. I think we talked about that, and we wanted to inhibit a lot of the freedom that users had, you know. So I don't think by the very design we could pass channels along channels. I cannot think of a way to do that, at least in the current design of MPL. And as it stands, the sequential and the concurrent parts of the language, they are fairly independent. Having a channel being determined by the sequential part of the language. Yeah, I have no idea how to do that. But
it seems like it is an advantage to do that though, because you have the ability to perhaps type check certain programs that you couldn't type check in a session type language because it is more static, right? There's less dynamic behavior that you have to account for. Right. And also because you have a situation where you can perform type inference and the fact that the protocol architecture is static means that you can handle like multiple parties, for example. So a big issue in session types is handling more than 2 parties. And how do you do that without either crazy amounts of annotations or dynamic checking? It seems like separating and restricting things in this way is an advantage to getting more out of the type system.
I think so. Yeah.
Yeah, I wonder if maybe backing up a bit, how do you think about the design space of this versus session types or other kinds of channel-based languages? Because obviously you're in sort of the same space of designs. What trade-offs are you making that other languages are not? Could you say something about that?
I think we consider ourselves a member of the session types, a family of type systems. Our type system, at least, to a degree, and as Ian asked in the last, commented in the last part, we are not able to write some of the programs. Our users are not able to write some of the programs because of how we have designed the language. But at the same time, I think it comes with a lot of type safety guarantees. So right now I have a weekend version of the type system implemented for MPL. If I were to implement the strong type system for MPL, I can provide the kind of guarantees that I don't think a lot of other languages can. For example, deadlock freedom guarantee.
So, and that, so forgive me, I'm not a session types expert, but typically session type systems aren't able to prove deadlock freedom. Is that what you're saying?
So for us, we have a very rudimentary notion of session types. We have channels, we have types for those channels, and the actions happening at the opposite end of the channel, they are dual to each other. That is all I'm taking session types to be. So maybe some of the nuances, for example, maybe session types doesn't mean deadlock freedom. If I have a definition for that, then by that definition, my language would not be a member of session types. Family of languages.
Right. I suppose I feel like we're talking past each other a bit. I suppose I'm wondering why why you made that design choice versus something that's like a richer type system like session types? Like what's the reasoning behind having this set of design choices versus what session types is? What's the differentiation, I suppose, is what I'm asking.
So a lot of the design choice, to be honest, was already made for me. This was work of my advisor, and a lot of the ideas are from his paper. So I think he wanted a language with as strong typing guarantees as possible, and doing things like sending channels along channels, things like that. It gave too much freedom to programmers, and they could essentially shoot themselves in the foot with that. So a lot of long answer short, I think they could I just based this implementation on the paper that was provided.
I understand. Okay, that's fine.
Yes.
Thanks very much for the talk. Just have a quick question, maybe. I'm kind of looking at this a bit from a sort of CSP, CCS perspective.
Sorry, what are those, CSP and CCS?
Yeah. Process algebraic sort of
Right, okay.
perspective. And these languages sometimes have features for refinement. So you can specify non-determinism, hiding. There's a notion of refinement. Actually, there's a whole kind of, tree of possible refinement notions. But also it kind of seems to me a bit, but this kind of monadic presentation is quite sort of close to code, quite operational. And there's actually some works where such a representation can be used to give a semantics to those more sort of refinement-based abstract languages. So do you see there's a place for this work, not just to be used for implementation and design, but also for modeling and maybe even giving a semantics to some of this higher level process algebraic notations? Or is that a complete kind of different pair of shoes?
To be honest, I really don't think I have thought of it in those terms. So can you give me an example of what entailing what that would be? Thinking of this in terms of CCS or CSP.
Yeah, I mean, you might start from an abstract model where you don't have the communication built into it yet.
Okay.
And then you apply refinement steps to slowly kind of evolve the design of the system, introduce processes. In your case, I guess it will be channels, so that the design patterns emerge, but you want to still be consistent with your high-level model of the system. So you have a relationship between the different layers of development, which is formalizable.
I have not thought of this language in those abstract terms, to be honest.
That's cool.
I suspect that it's too restricted to be used as a model for those sorts of things. I think that the like CSP and things like that are going to be more expressive, and not more expressive in the sense of like non-determinism to determinism, but expressiveness in terms of like channels on channels and things like that. Of course, they're not channels in CSP, but
Yeah. I think there's more expressiveness and less expressiveness in other cases probably. So, but I know some work where similar approaches are used based on monadic constructions, interaction trees, to give models to CSP processes, and they kind of look a little bit similar, and they have like similar trade-offs in a way. But I think that's a kind of complementary approach. I mean, once you're using a functional language like Haskell as a target, of course, you know exactly what it means. It has a semantics a priori, but you're kind of stuck in this sort of model somehow. But yeah, I can see that there's a much more restrictive use of parallel composition and sequentialism, things like that. Cool, yeah.
Great, I think there's probably, doesn't look like there's any more questions.